We'll demystify OpenAI's new Q-Star AI project and see how much closer we are to artificial general intelligence as the world buzzes with anticipation over this breakthrough for 2024. So let's dive right in, starting with two theories at its core: Q-learning and the Q-Star algorithm from the Maryland Refutation Proof Procedure System. Theory number 1, Q-learning to reinvent AI. At the heart of OpenAI's Q-Star buzz is Q-learning, which is a subset of reinforcement learning. This innovative approach enables AI to learn decision-making autonomously through a trial-and-error process akin to human learning. But unlike OpenAI's current reinforcement learning through human feedback approach, Q-learning operates independently, devoid of any human interaction. Just picture a robot navigating a maze. In this instance, Q-learning empowers it to autonomously discover the quickest escape route by experimenting with different paths. It's rewarded for progress and penalized for setbacks, gradually developing a strategy known as a Q table, which is a roadmap of optimal actions derived from its own experiences. Now contrast this with RLHF, where human intervention guides the robot's choices, influencing its path with suggestions or evaluations. However, with Q-learning, the AI reaches the coveted Q-star state, which is an ideal where the agent knows the best course of action in every single scenario, satisfying the complex Bellman equation. This likely means that if OpenAI's recent publication on training a model for advanced mathematical problem-solving utilized Q-learning, it will drastically improve the agent's native problem-solving abilities and extend ChatGPT's reach to unprecedented domains. But then there's theory number 2, the Q-star algorithm boost. Importantly, Q-star also refers to a component of the Maryland Refutation Proof Procedure System, which is a sophisticated AI theorem-proving technique that intelligently navigates problem-solving by combining semantic and syntactic information akin to piecing together a complex puzzle. This approach hints at OpenAI edging closer to creating AI systems with an even more profound grasp of reality, transcending mere text prompts to a level of understanding that is like a human. Understanding these nuances between Q-learning's environmental interaction and the Q-star algorithm's deductive reasoning enhancement is key to appreciating the potential impact of OpenAI's Q-star. But what can it do? Part 1. The potential of Q-star. While Q-star remains shrouded in mystery and speculation, its implications are quite vast for the AI industry. Should it represent an advanced form of Q-learning, we're looking at an AI capable of autonomous learning and adaptation in complex settings, potentially revolutionizing fields like self-driving cars. And if Q-star aligns with MRPPS's Q algorithm, we could witness a surge in AI's analytical and problem-solving capabilities too, impacting areas requiring deep reasoning, such as legal analysis, data interpretation, and medical diagnostics. Now, for both the benefits and the risks of this technology. In terms of benefits, the first is enhanced problem-solving. Whether as an advanced form of Q-learning or the Q algorithm, Q-star could lead to more efficient problem-solving AI systems across various sectors. The second benefit is improved human-AI collaboration. Enhanced AI capabilities could augment human efforts in research and innovation. Finally, the third benefit is the advancement in automation, with Q possibly even paving the way for sophisticated automation technologies, creating new industries and job opportunities. And the risks? The first risk to face will be the surrounding ethical challenges, with advanced AI systems raising significant safety concerns, including the risk of unintended consequences for humans. The second risk could be in terms of privacy, with the deeper understanding capabilities of these AI systems being able to pose heightened privacy and security risks to users who enter potentially sensitive information. The third risk is in terms of economic impact, as an advanced AI may lead to job displacement in certain sectors, requiring societal and economic adaptations. Finally, the last risk is that of AI misalignment with human interests, with the potential for AI systems to develop goals or operations that are misaligned with human welfare, posing an existential risk. Part 2. Q-star learning revealed. Q-learning is a type of machine learning used in reinforcement learning, where the Q signifies the quality of a certain action in a given state. It's about training an AI system, or an agent, to make decisions and learn from experiences, akin to how you learn from playing a video game repeatedly. The more you play, the better you become at figuring out how to win. Plus, Q-star learning combines Q-learning's decision-making prowess with the A-star search algorithm's ability to find the shortest path between 2 points, commonly used in games and AI. It's like teaching a super-smart robot not only to find the quickest way out of a maze, but to apply this intelligence to more complex problems, like beating a video game or solving real-world challenges. Critically, though, traditional large language models like GPT-4 depend heavily on vast datasets and are restricted by the knowledge within those datasets. Plus, they also struggle with context understanding and exhibit biases based on their training data. Moreover, once trained, they cannot update their knowledge, limiting their adaptability to a constantly changing world. In contrast, Q-star learning offers dynamic learning, allowing continuous adaptation based on new data or interactions. This leads to optimization of decisions and specific goal achievement, unlike the general-purpose nature of traditional LLMs. And here are the 6 critical roles of Q-star learning. Step 1. Environment and agent. In Q-learning, there's an environment, like a maze or video game, and an AI agent that learns to navigate this environment. Step 2. States and actions. The environment comprises various states and actions that the agent can take, like moving left or right or different positions on a board. Step 3. The Q table. This is the AI's cheat sheet, telling the agent the best action in each state. Initially filled with guesses, it becomes more accurate as the agent learns. Step 4. Learning by doing. The agent explores the environment, receiving feedback for each action. Rewards are given for positive actions and penalties for negative ones. Step 5. Updating the Q table. The table is updated considering both the current reward and potential future rewards. This approach ensures the AI thinks about long-term consequences, not just immediate gains. Step 6. Refining the Q table. Over time, as the agent explores and learns, the Q table becomes more accurate, making the AI more effective in navigating the environment. Part 3. The future and AGI. If it lives up to the hype, the development of Q-star learning could be a significant milestone in the pursuit of artificial general intelligence, as this new approach might address the limitations of current LLMs by enabling more dynamic, goal-oriented and efficient AI systems. In fact, the fusion of Q-learning with A-star search in Q-star could lead to AI systems that not only excel in decision-making, but also in navigating complex environments and achieving specific goals. The application possibilities are vast, from self-driving cars to AI agents capable of managing complex tasks. Meanwhile, Google DeepMind's Project Gemini is yet another promising AI endeavor that aims to utilize similar advanced techniques, with Gemini predicted to surpass GPT-4 across all benchmarks and reportedly exploring tree search methods akin to Q-learning in order to improve decision-making and creativity in AI.